In our series thus far, we've discussed the history and politics of Project Orion, highlighting the realities and myths of external nuclear pulsed plasma propulsion. We've tailored missions and designed vehicles to fulfill various roles in these missions. Something we've overlooked thus far is the design and manufacture of nuclear pulse devices for these vehicles. Our objective in today's episode will be to resolve the design challenges of small thermonuclear devices and arrive at a model practical for use on a first-generation ground-launched NPP craft. We will rely on some assumptions from previous episodes, so familiarity with our discussion thus far will provide some context. There exist different configurations for pulse units for different applications. We're specifically dealing with the interplanetary maneuver devices first, which are fusion-boosted devices with a range of outputs from 200 kilotons at 50% power output to over 500 kilotons at full output. In the absence of an atmosphere, nuclear detonations can be thought of as a flashbulb going off. With no material to transmit explosive force other than the low volume of fission products and plasma gas, most of the energy that would do work on nearby mass is instead expended as electromagnetic energy such as light and X-rays. At the core of the pulse unit is a thermonuclear device, producing radiation and explosive force transmitted through plasma or gas. Keep in mind this design will of course not be optimal, and in practice compression and lensing methods which are beyond our discussion will be used to reach necessary fissile efficiency. To respect this, we will over-engineer our design, so that we may have some certainty the device will function while not attempting to innovate over established designs based on public information. In reality, the total mass of each component will be lower. The smallest fission devices can be miniaturized to roughly the size of a grapefruit, but the lower limit of thermonuclear devices is somewhat larger. The 500 kiloton units contain a 25 kilogram device with a diameter of 15 centimeters. Of its total mass, 3/4 are 97% enriched plutonium-240. The remaining mass is primarily explosive lensing materials. Two types of high explosives with different detonation speeds are present: oxygen, also known as HMX, and cyclonite. It is possible to use alternative nitrocellulose-based high explosives if needed. The greatest engineering challenge posed in miniaturizing thermonuclear reactions is the high pressure of the fusion fuel needed to provide enough material to provide the fusion boosting effect. A small fusion cavity is desired to reduce the device's total size, but a smaller cavity requires exponentially more pressure to contain the required amount of fuel. Our 500 kiloton unit has a 4 cm diameter fusion cavity containing deuterium and helium fusion fuels under pressure at 2,200 kg per meter cubed. No more than 1% of the fuel will achieve fusion, but even at this low efficiency it will provide significantly increased energy output for the device. Minimum device output is around 200 kilotons of yield, or 850 terajoules of energy, and this can be reliably doubled via changes to the ignition timing. The thermonuclear device is only part of the pulse unit. To accomplish propulsive effects, other components are needed. The pulse device will produce a small shockwave of material, but before this can act on the environment in any way, the device has already generated most of its energy in the form of ionizing radiation and photons. The lower hemisphere of the nuclear device is shielded by a 4 cm thick layer of non-fissioning uranium-238. This material stops most forms of radiation besides fast neutrons. Dispersal of fast neutrons away from the vehicle is ideal, so this property of uranium is valuable here over alternative materials. The upper directional component of the pulse unit is made of beryllium oxide, which converts X-ray radiation into thermal energy as it is exposed to the fission cascade. The vaporizing channel filler moves rapidly upwards, creating a highly energetic cloud of plasma. This material transmits thermal energy into a tungsten propellant disc about 6 centimeters thick at the top of the unit. The tungsten propellant also becomes plasma, a state it will remain in well after it does work upon the vehicle. The properties of this propellant disc can be changed to produce different effects. A thicker disc creates a larger cone of high-velocity plasma, while thinner material produces a narrow jet of material. Less material also permits plasma to reach greater velocity. While tungsten is the material of choice for interplanetary propulsion units, lighter elements will allow for various other utilities. The pulse unit is assembled inside an aluminum drum, with fusing computers at the bottom and the tungsten propellant disc on top. A crumple zone built into the device's outer circumference protects the fusing components inside from direct impact. The outermost skin is a rolled anodized aluminum sheet, which is bolted to vertical structural flanges. Another sheet of aluminum with mounting holes is welded to the interface of the flanges, providing a rigid interface with the nuclear device. A gap between the inner and outer skin of about 3 centimeters allows the introduction of material pellets. Various types of pellet material are used to produce different types of plasma. The outer anodized surface can be painted with a rubberized paint to increase plasma generation as well. The pulse unit is exposed to space's strong thermal gradient for less than a second before detonation, so only immediate effects on the material need to be ascertained. Welding manufacturing prevents parts from slipping when subjected to thermal shock and reduces the number of total components per device. There are a few other considerations to the pulse unit's design. The device carries electronics capable of transmitting telemetry, timing control, and fusing. A thruster and reaction wheel combination can permit limited maneuvers if needed, but such additions should be attached as needed rather than being built into the standard unit. The pulse unit should be as simple as possible for both ease of manufacturing and reliability. Each pulse device carries a fusing computer, a communication antenna, and telemetry sensors. The unit is able to detect its own rate of rotation using a miniature gyrotachometer and relative speed using a laser rangefinder, which returns data on distance to the mother craft. This combination of onboard sensors serves as a redundancy to the remote fusing system normally used to trigger the unit. Unsafe operation can be interrupted using several methods. The parent vehicle can interpret an unsafe situation and disable the fusing sequence remotely, or the device may disable itself using data collected from its individual sensors. Should the device not receive a fusing command from its onboard computer or the parent craft, a physical failsafe will kick in after a predetermined amount of time. Once a standard pulse unit is activated and fired from the ship, it begins a countdown. If the device fails to detonate for any reason, a pressure valve will open, causing the pressurized fusion fuel to escape the device. This renders the device safe and prevents both fission and fusion from occurring, reducing the device's explosive yield to a few kilograms of TNT. The goal is for all pulse unit production to occur in space using as much locally sourced material as possible. Any material we cannot source from the lunar environment must be imported from Earth. We have a fairly simple problem before us from a manufacturing perspective. Obtaining enriched nuclear material beyond Earth is not inherently difficult. The challenge of imagining these industries lies in understanding their logistical and operational needs, something that has not received extensive public study. There is a strong case for enrichment in space being much simpler and cheaper than on Earth using understood technologies. That being said, we do not have accurate projections of the capabilities of such activity, and a need exists to develop enrichment methods for the space environment. Reprocessing and enrichment do not have a tested paradigm for industrial-scale activity in space, but performing enrichment in microgravity removes many obstacles to the process we face on Earth. The most common technique for enrichment relies on a large number of centrifuges operating in sequence. These systems are expensive and difficult to manufacture and maintain on Earth. The process of enrichment relies on high-speed centrifuges operating at tens of thousands of RPM. Due to the destabilizing effects of gravity on a rapidly spinning centrifuge, very close tolerances and precise tuning of weight is needed. Because the centrifuges are linked by plumbing for the uranium hexafluoride gas to travel between them, the centrifuges operate in large arrays and must be carefully assembled to eliminate the smallest vibrations. When assembling a centrifuge operation in space, the individual centrifuges do not need a rigid connection and can float on thin, flexible mounts. The most important engineering challenges to reprocessing on Earth do not apply in microgravity, making this activity desirable as a basic industry. While the exact methods will need to be tested, there is an opportunity to use smelting products from lunar resourcing operations directly as a material source for producing uranium. The ability to source radioactive material from Luna and enrich it locally is highly feasible given the expensive alternative of stacking rockets with payloads of heavy metals. It's likely that industries on Luna will already rely on a diversity of centrifuges to sort gaseous smelting products, since centrifuges are more efficient in microgravity and mechanically simpler than alternatives. The equipment used in enrichment can also be used in industrial tasks such as fractioning, distilling, and molecular separation. We have an established context for enrichment industry off-Earth. Lunar regolith will be processed using stages of smelting and fractioning, producing uranium oxide. This product is converted into uranium hexafluoride gas, which is fed again into the fractioning centrifuge to separate it into three products: enriched uranium-235, depleted uranium, and uranium-238. The enriched uranium can be converted into uranium dioxide for power production applications, or taken in its pure form in the manufacture of pulse units. The lunar regolith is well suited for processing using fractioning centrifuges, which can sort through both gas vapor and molten material simultaneously. At this juncture, we should be aware that mining activity on Luna using all realistic methods will generate non-trivial amounts of uranium oxide, along with a slew of other less commonly found elements. This material will need to be used or stored, even if nuclear material is not in demand by industries. The maturation of technologies associated with lunar mining will mean an eventual expansion into enrichment. Even if nuclear material is not sought after on Luna, there will still be a necessity to reprocess nuclear waste material from power production industry. The adaptation of reprocessing technology to space is inevitable, and we ought to consider this in our current discussions of interplanetary infrastructure. Industrial-scale breeding of uranium into plutonium will be necessary for sustainable nuclear pulse deployments in space. Without going into too much detail on the process of nuclear fast breeding, understand that producing plutonium is not an energy-intensive task and can be accomplished using a natural uranium or powered fission reactor. This means it is fairly inexpensive to produce plutonium from unenriched or natural uranium ore. In space industries, it is likely all uranium in circulation will be either enriched or a product of enrichment, such as uranium-238 or depleted uranium, and not natural uranium ore. This paradigm is unlikely to change in the near term unless ample uranium ore sources are located on the Moon. There are some places in the solar system beyond Earth where natural uranium reactors are feasible, locations where the geology allows for low-cost, dedicated uranium mining. Mars could facilitate this development, where a technique known as in situ leach mining allows extraction of uranium from sandstone aquifers on Earth. This low-impact mining approach allows rapid extraction without digging pits or mines. The mining is accomplished by pumping water combined with leaching chemicals into a sandy deposit and then siphoning the water and sedimentary material out for distillation. We've brought up the potential for Martian and natural uranium industry in order to illustrate that plutonium can be easily produced at any location where this is happening. Any location where natural or enriched uranium is being utilized. Mars has the same uranium-rich sands locked in its dried-up aquifers that we have on Earth, and there is just a matter of locating them before they can be harvested using proven methods. We've resolved the fundamental questions of manufacture, logistics, and sourcing, so now we ought to delve into the plethora of options open to us using this instrument. We can accomplish a lot with a nuclear reaction, although for half a century, the weapon's applications were the only ones tested to their limits. Historically, perhaps the most well-known modification to the Orion Pulse unit became known as the Cassaba howitzer. Named after the cassava honeydew, because the scientists at Lawrence Livermore National Lab were, quote, on a melon kick that year, this concept was the fruit of an effort to conceptualize an Orion Pulse device as a weapon. The Kasaba howitzer replaces the tungsten propellant of regular devices with a thinner layer of lighter material. This material is turned into plasma by the nuclear device, which allows intense X-ray and visible light to pass through. The intense light and X-ray radiation impacts a metal structure embedded with fragments of fissile material. This method allows optical pumping of a laser media, resulting in a powerful, narrow laser beam with similar cross-section as the particle stream initially produced by the device. In light of the unit cost and laser energies produced, these devices were deemed too inefficient for further consideration. The Kasaba howitzer concept relied on ideas originating in Project Excalibur, a development program hoping to provide laser defense against ICBMs from orbit. Excalibur proposed a single, non-directional nuclear device, which would be used to pump a spherical array of lasers, each which would be independently aimed at a missile target. The Kasaba howitzer, as well as Project Excalibur, are both examples of a formal study which proves the diverse capabilities of small nuclear devices, and were both canned for being too expensive for military application. Without the context of widespread military application, the economic value of these devices is less questionable. Military space technologies must be maintained for decades and work with near-perfect reliability at any time. They must be manifested through extant military-industrial organizations, meaning building large fleets of autonomous nuclear-armed space vehicles becomes expensive very quickly. A realistic nuclear-pumped laser satellite network would require thousands of vehicles to function properly, so it's easy to see why this kind of project had a price tag of well over $50 billion 1980 dollars. We've discussed in previous episodes how the conversion of weapons material into utility devices offers strong economic incentives for private companies and the military complex alike. There are two fundamental ways in which military and utility devices differ in economic terms. Firstly, the cost to produce utility devices is dramatically lower due to the simpler requirements of non-military systems. Secondly, the measurable economic benefit of fielding utility devices is magnitudes greater than even the best-case scenario use cases for military systems. Military systems will need to be assembled on Earth into vehicle payloads, launched into orbit, maneuver into position, and perform station-keeping maneuvers for perhaps decades, all while keeping its nuclear devices in perpetual standby. Utility systems, on the other hand, will be fabricated in space or on the moon, and can be kept disassembled until needed. Even if deployed on a ground-launched Orion, the large total number of devices is a more manageable industrial task, since they will not need to be as lightweight as would be necessary on a chemical launch vehicle. Military systems exist within a threat management paradigm, where the system may be deemed effective even if it never performs its task. Utility systems produce immediate economic value. They excavate ground, they gather data, sinter regolith structures, shape metals, and if used with regularity, represent a demand which space industry is inherently positioned to satisfy. Recall our discussion earlier in the series about specific use cases for NPP devices. There are applications in imaging, excavation, chemical production, smithing, mining, and manufacturing. We'll investigate exactly how changes to the device permit these various functions. A typical interplanetary pulse unit's inner fusion fuel can be removed and replaced with a plug of low-enriched uranium. This removes all thermonuclear function, transforming the unit into a pure fission device. The low efficiency of the hollow-core fission device generates diverse long-lived fission products. Pure fission mode is useful for mining, since radioactive material can be treated as another component of mining slurry, which already contains natural uranium and transplutonics. In the imaging configuration, nuclear devices are modified to produce useful wavelengths of electromagnetic radiation capable of imaging dense atmospheres. In this configuration, the propellant disc is a layer of 8 cm thick of thermoplastic embedded with beads of steel alloy. The density of these beads determines the total X-ray output of the device, since they convert X-rays into thermal energy, including visible light. The device can also be converted into a directional nuclear-pumped laser with ease. The propellant disc is replaced with a long tube of lasant material. This tube is surrounded by a focusing cone of laminated metal fibers. The cone focuses X-rays from the detonation into the horizontal surface of the laser tube, provoking a cascade of inverse energy states which generate a powerful X-ray laser along the vertical axis. A ring of ferromagnetic material coated in fragments of uranium focuses the laser beam in the direction of the target. Metallurgical operations involve the heating, hardening, and shaping of metal parts. A range of thermal energies can be produced depending on the task. The goal of this configuration is to limit the production of gamma and X-ray photons, with most energy represented as ultraviolet and visible light. These effects are accomplished using a 33 to 50 centimeter thick propellant disc of layered aluminum and copper. Residual plasma will wash over the target object, leaving some of these metals behind as deposited vapor. The question of residual material on working parts is a good point towards a wider question. How can we reliably sinter material using direct transfer of nuclear thermal energy in space? Once again in our series, we'll establish a sequence of events to explain the process of nuclear smithing in a specific and realistic scenario. While smithing operations will play out differently in various locations, we'll look at an operation involving a work area on the surface of the Moon and an orbital vehicle deploying the pulse units. This is a sintering operation, where a set of metallurgical pulses will be used to thermally fuse several hundred square meters of aluminum dust into semi-finished parts. Consider the interface between these two construction tools. The work site is at a static position on the lunar surface, and the NPP construction vehicle is in orbit. The vehicle will pass over the site about every 2 hours. Because the craft will remain in the same orbital plane, it can deploy a number of pulse units behind it, which can be then timed to detonate in succession, allowing for continual pulses even when the vehicle is not directly overhead. These units do not carry maneuvering systems, having only a small gyroscopic stabilization system to point them in the right direction. This pointing capability means pulse units can drift off course under the influence of irregular lunar gravity and will still perform as long as they remain pointed at the construction site. The majority of energy responsible for the sintering process can be reflected optically and will naturally reflect off the lunar regolith and the sintering material. This means reflected light and heat energy can be captured using thin reflective sheets arranged vertically around the work site. A fine layer of powdered glass increases the reflectivity of the regolith as well, allowing for much of the ambient energy to be recycled. Recall that without atmosphere, all heat is being transferred via direct irradiation, so controlling the amount of reflection can increase working temperature of the sinter bed substantially. Reflection is the main mechanism for controlling temperatures in the sinter bed throughout the operation. The reflective sheets can be partially removed to lower the overall working temperature when needed. The method of nuclear sintering we've outlined has potential complications arising from the use of high-energy plasma. The finished pieces will contain vapor residue composed of aluminum and copper. These finished pieces will contain vapor residue composed of aluminum and copper. These impurities naturally gather at the surface of the molten sinter metal, and they may allow oxidization to take hold and spread, ultimately compromising the material's strength. There are many other challenges such as this that must be interpreted and understood before these methods can be applied. Thank you for watching. I hope you enjoyed today's episode. Please like, subscribe, and comment to help grow our audience. Thank you.